Okay, so in this video, we will introduce you to uh, diastereomers and also meso compounds. So first let's recall the classification of isomers. Isomers can be classified as constitutional and stereoisomers. Among stereoisomers, there are two divisions. One is enantiomers and the other is diastereomers. In earlier section, we saw that isomers can be classified as constitutional and stereoisomers. Stereoisomers have the same connectivity, but they have different spatial arrangement, and constitutional isomers can differ in connectivity. This can be further subcategorized as enantiomers and diastereomers. Now you are familiar with enantiomers, which are non-superimposable mirror images. Let's familiarize ourselves with what are diastereomers. Now, diastereomers are isomers which are not mirror images. So, for example, if you take a cis-trans isomer, this is 2-butene, this is a cis isomer and this is a trans isomer, they are stereoisomers, but they are not mirror images of each other. So therefore, they cannot be enantiomers, but they should be what are called as diastereomers. Okay. Now, the major difference between enantiomers and diastereomers is that enantiomers have same physical properties. However, diastereomers differ in physical properties. The difference between enantiomers and diastereomers can also be seen if we take another example. Let me draw this out. It is a substituted cyclohexane molecule. So I'm going to put two groups here, say an OH and a methyl group. Okay, so this is my original compound. Let's see if it does have any chiral centers or not. Okay, so I will, if you look at this carbon atom has 4 different groups, so we have a chiral center here, and then this one also has a chiral center. Okay, this carbon is also a chiral center. So diastereomers are when we have more than one chiral centers. Okay, diastereomers happen only when you have more than one chiral centers. So in addition to the cis-trans isomers, okay, here we do not have any chiral centers, but then these can be called as stereoisomers, which are not mirror images, so they should be diastereomers. Okay, but here we have these chiral centers, more than one, and there are different ways by which we can draw them. Okay, based on their stereochemistry. So I'm going to draw this as here. I can have the OH in one case pointing up and the CH3 also pointing up. If I draw the mirror image of this, what will it look like? I will have the OH pointing back and CH3 pointing back. So these are the mirror images of each other. I can also draw a structure where OH is pointing up, however CH3 is pointing down, and then the mirror image of this would be where the OH is pointing down and the CH3 is pointing up. Correct? So the relationship between these two is that of enantiomers, and the relationship between these two here is also enantiomers. Okay, let's label them. Let's call them as A, B, C, and D. This is A, this structure B, structure C, and D. Okay, so now A and B are enantiomers. Similarly, C and D are also enantiomers, right? Because they are mirror images of each other. However, what the relationship between A and C, or B and C, or A and D, and B and D, right? If you look at A and C and B and D and B and C and A and D, they are not enantiomers. However, they are isomers of each other, right? So these are what are called as diastereomers. Diastereomers. They are not mirror images of each other, but they do have a isomeric relationship with each other, right? So A and C, or B and C and C and A and D and B and D. These are all diastereomers. So if you try to assign the absolute configuration, we can write that down. I'm not going to go through this whole process, but just write it down here that, if you look at this is 1, 2, 3, so this has to be R, okay? And here again we have methyl here, so we have the priority group this is 1, as 2 and 3, so this is an S, right? So we have S here, R and S. Since this is a mirror image, this should be S and R. And then here, since the OH has not changed, I know that this is still R, but see, CH3 has changed, so this is S, R, this is R, this one is R. Okay, so that's an R. And here we have an S, and then we have a S here, right? So R, R, and SS, these are enantiomers because their stereochemistry is completely reversed. R, S, and SR, these are also enantiomers. Okay, but like we said before, the relationship between A and C and B and C and A and D and B and D is that of diastereomers. Okay, so what else can you conclude from this? That if they are enantiomers, the chirality is reversed at all chiral centers, right? Among enantiomers, you can see that the chirality is reversed at all chiral center. R becomes S, this R becomes S. R becomes S, and this S becomes R. Okay, but in diastereomers, the chirality is reversed at some centers and it is not reversed at some other centers, right? So if you look at A and C, which are the diastereomers, right? We have R here and R here, so the chirality did not change there, only S became R, right? So we can make a conclusion that for enantiomers, chirality is reversed at all chiral center. Chirality is reversed at all chiral centers. And for diastereomers, the chirality is reversed only at some chiral centers. Chirality reversed at some chiral centers, not at all of them, okay? At some chiral centers. And diastereomers have diastereomeric relationship you see when you have more than one chiral center. Okay, there could be an example where you have 3 chiral centers or 4 and so on, but when you have only one chiral center, then we are not looking for any diastereomers in those molecules. Okay, all right. Let's also discuss another possibility of what is called as a meso compound. Okay, now it is not necessary that all molecules which contain chiral centers be chiral in nature. Okay, they can be achiral too. So that's what we are going to look at examples. So let me draw this molecule. Okay, so if I have a structure like this, where I have, say, just 2 OH groups here, okay? And I'm going to draw the different isomers that's possible. So before I move on to this, there is a general formula that if you have n number of chiral centers, then the total number of stereoisomers can be derived from 2 to the power n. So in this case, if you have 2 chiral centers, we have 2 to the power 2. That means you will have 4 stereoisomers. Okay, 4 stereoisomers. But that may not be necessarily true if your molecule is also a meso compound. Okay, so in the previous case, let me go back to the previous page to show you. In this case, see, we have 2 chiral centers, right? So if you add the 2 to the power n formula here, we have 4 stereoisomers, which are, this is 1, 2, and we have 3 and 4, right? So this stands true in this case where 2 to the power n represents the total number of stereoisomers. Okay, but in the next example that I have, let's draw out the different enantiomers that can be possible here, which is where I have one OH pointing up and the other OH pointing down. In one case, its mirror image would be where I have this OH coming down and the other OH pointing up, right? These are mirror images of each other. And I can also have another stereoisomer where both the OHs are pointing up, and then the mirror image of this would be where both the OHs are pointing down. Okay, but if you look at this case here, this represents a pair of enantiomers, right? Because they are mirror images of each other. However, if you look at this bottom structure, even though it has got chiral centers, there is also a plane of symmetry. Okay, here we have a trans compound, right? The relationship between the two OH is that of trans. Here the two OHs are cis to each other, but that brings a plane of symmetry in the molecule, as a result of which these two are not enantiomers, but they are identical. They are similar structures. Okay, they look like they are enantiomers. However, because of this plane of symmetry, you also only have they both are actually the same. They are the same structures. So this is an example of what is called as a meso compound. Okay, so that means they do have chiral centers, but they also have a plane of symmetry. Okay, another example would be like this, right, where I have 2 methyl groups. So they do have chiral centers, right, but then in the cis compound, so we can draw the cis, and its mirror image would be where I have the 2 CH3 groups pointing down, and then I have the trans, right? I have the trans where I have 1 CH3 here, 1 here, and then the mirror image of that would be this going down and this going up, right? This is my trans and this is my cis. Now, which one would have a plane of symmetry, the cis or the trans? It will be the cis, right? Cis has a plane of symmetry, whereas the trans cannot have a plane of symmetry because you have 1 CH3 pointing down and the other CH3 pointing up. Okay, so here these two will have a enantiomeric relationship. So these are enantiomers, but here these represent a meso structure. So ideally, this molecule, which has got 2 chiral centers, we expect it to have 4 stereoisomers. However, it only has 3 because these both are actually the same compound. So we have 1, 2, and then a third compound which has a plane of symmetry as well as chiral centers in it. So this is what is a meso structure. Sometimes it kind of is a little bit difficult to figure out which one is a meso structure. So one thing you can look for is that if you have 2 chiral centers in your compound, then the stereochemistry will be opposite for both of them. Okay, so for example, if this one, we have this example here, right, you can see that this is R, right? This is R here, right? And here, if you look, this should be S. And so at the 2 chiral centers, the stereochemistry is always opposite in a meso compound. Okay, so that is kind of a little hint for you to identify a meso compound, right? So summarizing, we have enantiomers, diastereomers, and meso structures. Enantiomers have exactly the same physical properties, so it is difficult for us to separate them. Diastereomers, they can have different physical properties, so it's easier to separate diastereomers. Okay, so in the next video we will talk about optical activity and also how to separate out enantiomers. That process is called as resolution, and we'll talk about that in our next video.